students are slowly going to join. So it's a pleasure to have Professor with us today. He's a professor at University of Malaya, and his formal MS was from Nanyang University, and then formally did his PhD in the University of Constance. Subsequently, he has his area of research is actually optics, quantum optics to be precise, light matter interaction, and he has, he has been involved in many of these international conferences. One of them, my students have gone, but I could not go. This time probably there was something which got postponed. So he's a well-known figure in the international level. If you look at his works, the works are truly amazing, and particularly in light matter interaction is quoted. So now I request Professor Wee to deliver his talk. Talk is for 1 hour and 30 minutes. 1 hour for your talk and then for leisurely discussion. So please start your talk.
Okay, thank you very much, Professor Pasantra, for the invitation to give a talk in this wonderful conference, online conference. I am very glad to be here to share my work with all of you, and thank you for your time in this afternoon. So I organized the conference Grand-O 2018. I'm glad many came, and also to 2019. But this time, due to the COVID, we have to postpone. Hopefully, after things recover, we will have we'll continue with the Q&O on site. Okay. So today my talk is on the correlated double Raman photon from single atom to mesoscopic particle. Our research group is quantum and laser science. We do mainly theory and also some experiment with femtosecond lasers. These are my research interests. And if anybody interested, feel free to contact me. Yeah. So this is some overview of our lab. There has been some renovation. The man behind the financial support of that give rise to the construction of the lab is our former Vice Chancellor. So, as we know now, this quantum nonlinear optics is a very hot topic now. Is from using quantum effects of interaction of photon and atom to mesoscopic particle, and it make use of the quantum coherence, so-called Photonium material. And the nice thing about quantum nonlinear optics is the strong coupling. And there are various methods to establish strong coupling. And with the strong coupling, a lot of interesting nonlinear optical effect can be achieved at single photon level. And this is important, has important technological consequence of shrinking the devices and making quantum technology possible at a small scale. This will be quantum integrated circuit, things like this. Quantum integrated optoelectronic connection. So my focus will be on the quantum theory, especially on the quantum Langevin, which makes use of quantum system coupled with a quantized photon. And this is
we can't see your slide.
Oh,
you have not shared your slide.
Oh. Let me check. Maybe I would Can you see now?
Not yet. Have you shared screen? Share screen. There is a green button on the Zoom. So click on that and then select your screen.
Oh yes, I forgot. Okay, can you see my screen now?
Yes, sir. We can see your screen now.
All right. Okay, these are basically the picture I introduced just now. Can you see the full screen? Is there anything blocking?
Yeah. We can see your screen now, full screen. Yeah.
All right. So this is our lab, and the previous one. Okay. So now, basically, my focus will be on the quantum Langevin theory with the quantum system interacting with quantized field plus noise operator and with non-linearity effect taken into all orders. And the output of the photon pairs can be controlled, which means we can control the quantum spectrum as well as non-classical quantities such as G2 and entanglement. Yeah. So I will show the theory for several fundamental systems, from single atom to two atom and mesoscopic particle. As we know, there are many measures of non-classicality. So one is the Mandel Q factor, which characterize whether the radiation is thermal or Poissonian or like a laser, or sub-Poissonian, which is non-classical. And the squeezing effect is also another way of determining the quantum properties. We also have Wigner distribution function. When we have a negative VT, then it indicates the non-classicality. And in many single photon interference, when we have a destructive interference of two photons from each arm of the interferometer, this Alexander interferometer, when there is a destructive interference, we also say that this is there's non-classical quantum effect. So as you see, there are many measures of non-classicality depending on how we look at it. So in nature is really many phases depending on how we look at it. So there is actually no definite answer. We can look at it one way and we can say it's non-classical, and we can look at from another way it's non-classical. So, but it depending on our needs. But in this case, we are more interested in double Raman scheme, where we need to understand study the photon correlation, the non-classical correlation between photon pairs, because this can be used in quantum information technology. For example, in quantum teleportation, at a far distance, we need to store information, and then we from a photon store into a quantum coherence, and then later we'll retrieve with on-demand retrieval of the photon, and we need to ensure that the two photons, the input photon and the output photons, they are correlated, and means that the quantum information is preserved as much as possible. We can look at this from the angle of fidelity. We can look at it from angle of photon correlation also. So in this famous work by Looking and Fleischhauer in the 2000s, they study a lot about this double Raman scheme. In the sense of dark state polariton, they show that the photon couples strongly with the atomic polarization can form the so-called dark state polariton that has a well-preserved properties, can be stored inside the medium, and later can be mapped out with the laser. So a lot of work have been done after this with the double Raman scheme. In 2003, there were two landmark experiments. This experiment showed that it is possible to maintain the photon correlation between the photon that is stored, the input photon, and the output photon, with high level of correlation. So these two experiments has sparked further work. So especially we were interested, so we did a lot of on this photon correlation from the single atom to driven by CW laser to the case of driven by laser pulses. And then we also have two atoms with dipole-dipole interaction. And then array of two photon emitters. And then we extend to medium with many atoms, where propagation effect is taken into account. And then we have mesoscopic particles, like the simplest one is a spherical particle. And also we study the effect of quantum noise, and also correlated two photon lasers. So our interest mainly on novel non-classical light source can be used for quantum communication and many other quantum technologies, such as microscopy and also potential lithography. And these are the topics I will focus on. And there, in terms of theory, there have been a lot of our theory view on the work of previous researchers, especially Professor Roy Glauber, Nobel laureate, Steve Harris, and then John Zantier. They have done earlier work on the G2, and then also using the Heisenberg-Langevin approach by Davidovich, Raman, Glauber, and Hake. And in terms of strong interaction from in the quantum nonlinear regime, Professor Agawa, who is one of the speakers here, Boy and also Shen and Manaskali, they have also contributed in this. In this work, I have no time to present this. This is the work on the quantum plasmonic, which I have also done. But this is maybe another topic. Mainly, we are interested in how the effect of microscopicity. So there has been some work going on, microscopic effect on quantum and non-classical state of light using room temperature diamond. This is mainly in the context of quantum memory. Quantum correlation of light is also interesting for quantum metrology, especially in detection of gravitational wave and also sensing of very weak gravitational field. The interesting aspect is in the quantum memory. As we know, the distance of QK of quantum information transfer between two parties has been increasing. The distance is now beyond 100 kilometers with fiber. We have to make use of the quantum memory as a part of as an essential essential device in the quantum repeater. So to ensure the technology is built on solid fundamental scientific fundamental, we need to understand all the basic physics, quantum physics, especially the non-classical properties of light. The earlier work of these people, they found anti-bunching of a single atom in resonance fluorescence. So this is a very nice experiment with the data fit quite well with the theory. And if you have a beam of atoms, sodium atom, this is a single atom, these are many atoms, then you still have anti-bunching, but it does not start from zero, which it seems to have this dip is not perfect. And there has been many other ways to control the anti-bunching, but it's fundamentally resonance fluorescence we cannot control very much. So there is, in this paper, they are using some kind of phase filter to control the parametric down conversion in type 2 crystal. So our work will be based on double Raman scheme, which is here is a single photon and two photon, and then many from single atom, two atom, and then the rest are mesoscopic particles. So in this work, we have done theoretical calculation for double Raman scheme using Schrodinger equation approach. And we find that in this double Raman scheme, first Raman is spontaneous Raman, and the second one is resonant Raman. So if we have any other Raman scheme, would not be able to produce high non-classical correlation like this. So only this scheme can produce very large G2 and with anti-bunching here, anti-bunching, and also with the oscillation. Compare with the cascade scheme, which is typical of the parametric down conversion. So in the parametric down conversion, there is no anti-bunching. So even though there is entanglement, the parametric down conversion is used to produce entangled photon pairs, but there is no anti-bunching. So that's why I say it depends on how you look at it, what you want to use. So it can be, classicality is always very subjective, depending on what quantity you look at it. Okay. So in this case, you can control the control field. If you have strong control field, you have oscillation. So this oscillation period depends on the inverse of the Rabi frequency. So the picture here can be explained by the splitting of the outer-tau splitting of the level A, and this gives rise to the quantum interference of the anti-Stokes photon, and therefore the oscillation of the G2 between Stokes and anti-Stokes. Okay. So here is a bit to show you the theory. Effective Hamiltonian, the first is this spontaneous Raman. The G is a spontaneous Raman term, is coupled between B, C, and B. And then the resonant Raman is this term, and followed by the anti-Stokes photon. So we want to find the correlation between the Stokes AK and the anti-Stokes AQ. And we use the state vector approach, and after going through the standard calculation, we can compute the G2. Okay. So as we know, spontaneous emission is a quantum effect that is present anywhere, microscopic or macroscopic. So we have to include it. And we want to study the quantum nature of the Raman photon pairs and how it varies in the microscopic and microscopic regime. The photon pairs in the microscopic regime can have two contrasting features depending on the scheme. For example, as I have shown, there is photon bunching in the cascade system, but we have photon anti-bunching in the Raman scheme. This RED means Raman, we call it a Raman emission doublet. The previous result that shows the anti-bunching with oscillation. Anti-bunching, as defined by this, the gradient is positive near the zero delay. This is a consequence of destructive quantum interference. Destructive quantum interference and oscillations, they are the manifestation of the quantum or wave nature of light. Okay? So all this can be explained. And from the single atom case, it would be tempting to extend it to two atoms case with the dipole-dipole interaction. So the simplest is to consider the two-level system for two atoms. So we can start with the Hamiltonian, standard Hamiltonian, atom interacting with the vacuum with no driving field, only the vacuum field. And then we have the state, we write out the state vector, initially in the ground state. There are few possibilities. Initially, we can assume one atom in the ground state, one in the excited state, or both in the excited state. But this is the general state vector. If both excited, no photon. And this is two photon, one photon K, one photon Q, and both are in the ground state. And these two are, one of the atoms is excited and with one photon. So with this state vector, we can solve for all the coefficients, and we can study how the dynamics of the two atom system, and also to compute the G2 correlation function. Okay. So in the basis can be pictured in this manner, the four bases, okay, of the state vector. If we can look at it from the dress state picture, where one is the bright state, one is the dark state. basically this is shifted a bit from the middle. So, and the line is also different. The line width is also different. One is super radiant, one is sub radiant. So if you solve exactly, we can find that the decay rate for the two, for the plus and minus, plus is the bright state, dark minus is the dark state. They are given by the G factor here. So this is the real part. The H part is the so-called the lamp shift part. This is actually well known. Given and the terms or the Bessel function are due to the interparticle distance. Okay. And there are two possibilities. One is perpendicular, dipole perpendicular to the field. Another one is a parallel. Yeah, there are two polarization. Okay. So we can study now the G2, the two photon amplitude. We can derive the two photon amplitude, and then from there we can compute the G2 function. Okay, the psi B psi A is given by this. That means one is one atom emit one photon to one of the detectors. Okay, and the other term is just interchanging the A and B. Okay? So because we have two detectors now, that's why there are two possibilities. And this is quite kind of well known. Okay, one atom obviously, if it's excited in the two-level system, can only emit one photon. Okay, these possibilities they are expected. But in the case of small interparticle distance, we also have additional properties. That means like one atom can emit two photons, one to one detector, and this seems counterintuitive. But actually, this can be explained as due to excitation by one another the neighboring atom. So after this atom emit, it is excited by this atom due to the dipole-dipole interaction, and then you can emit another one again. Okay, so the calculation automatically, all the terms will come out nicely, and you just need to interpret the term based on this diagram. So when you compute the G2, you can get the result correctly. Okay, another possibility is we can study the intensity of, instead of G2, the intensity of emission or probability of emission. If the states are entangled, okay. Now this is plus minus, they are the entangled state. The superscript P is to remind us of this factor. We can have 100. No, this is initially it can be 50-50. We can adjust it. Also more important is the phase here. The phase exponential ik not R1, R2. It reminds us of the spatial interference. They are indistinguishable by spatial location. Okay. So So far, so good. Anybody has any question? Or is there any, can everyone hear clearly? Yeah. Okay. So I will just proceed. From there, we can compute the intensity intensity from by computing the coefficient CK. Okay. So, and this intensity will give interference effect. Okay. Initially, there are two possibilities. One, we can include the phase or without the phase. In the case of initially entangled without the phase, that means the theta, this angle theta is this. Okay, 90 degrees means you have the detector perpendicular to the interparticle axis. Okay, in this case, there is no, the phase is cancelled out, they are all the same phase. Okay, so you have the intensity versus time, it will go exponentially, it will damp exponentially, but it will also vary with the interparticle distance. In the case of anti-symmetric, we have a dark state for a very short distance as expected. So dark state is ideal. If you increase the distance, then no more dark state. Okay? The negative state will decay on. Okay? So, and now if the detector angle is 0, then the phase exponential ik not r1, r2 becomes very important. It gives rise to this oscillation. At some interparticle distance, you can see signal. At some interparticle distance, no signal. So the state is very important. The phase, how you prepare the entangled state, the phase is very important. Okay. We can also study the radiation pattern. But more, what I want to focus is on the G2. Here is the G2, the result for G2. Okay, in this case, the detectors are here, A and B, and then we calculate the G2. So the G2 as a function of time and also interparticle distance. For short interparticle distance, we find some curious features. Okay, so we magnify this region. Is less than a quarter of wavelength. Okay, so in this range, very small, we can see very fine structure here. It may be useful for sub-wavelength imaging. Okay. This work has been done by Professor Zubairi and Professor Agawa also on sub-wavelength imaging and resolution beyond the diffraction limit. If we take a closer look at this region, okay, here, this region we magnify some more, which is between here, exactly at 0.5, which is quarter of wavelength, the interparticle distance, we can see anti-bunching. Okay? So this anti-bunching going up and down. Okay, and this can be explained by the wavelength can fit in like this. You have the interference, destructive interference exactly. So there is no signal here. Okay. When the detector is at 90 degrees, then nothing interesting you can see. Okay. Without the G2 is just exponentially damped. All right. Okay. So we can also study the G2 as a function of angle, okay, angle of emission. Okay. All right. So from the two-atom, two-level system, now we can also study two-atom double Raman system. Okay, two atom, but now each atom is a double Raman system. Okay. We can proceed with the same formalism and we can have all this the same picture, right? But now instead of one photon, we have two photons, which is a Stokes and anti-Stokes. Stokes and anti-Stokes. All right. So now the possibilities increase by 2 times, because now we have the two photons and it's a Stokes and anti-Stokes. I will skip the formalism, which is using is the same using Schrodinger picture, but just to show you the result here. In the double Raman scheme, you still have the G2. You still have anti-bunching, or the oscillation anti-bunching as a function of the laser field, the control Rabi frequency. As you increase the Rabi frequency, the oscillation becomes more rapid. But here, the focus here is not on that. We want to focus on the sub-wavelength. The R divided by lambda is less than 0.1. So in this region, it seems that there is no signal, almost no, the signal is vanishing. Okay? Because of the dipole-dipole interaction, the G2 correlation is nearly suppressed, and the oscillation becomes more rapid. It does not follow the conventional physics that we have understood earlier. Okay, so if you have depending on your detector angle, 90 degrees, this 0 degrees, the G2 map as a function of delay and also interparticle distance, they are very different. You see the pattern. So the 3D plot is very helpful to give us the whole picture. In this case, when R divided by lambda less than 1/20, the correlation almost vanished. This is due to the coherent effect. That means the two atoms will talk to each other. They don't talk to the detector. They don't emit to us anymore. They emit to each other. It's like a couple. They are in love. So they are talking to each other. They are focusing on their business. All right. So this is the interesting effect when we have a many particle case. All right. So now I want to emphasize the importance of fundamental theory in our work, related to our work. One is the Weisgrauber's photon correlation. His formalism has enabled us to compute the joint detection probability in a quantum sense correctly. That is the revolution in quantum optics. The earlier one was the quantization of electromagnetic field, and this gives rise to the quantum nature of light. So these two developments have given us quantum optics, and it's thanks to them. Actually, the quantization of electromagnetic field is due to Dirac. And also the invention of laser has enabled us to study a lot of control atomic system. And this is the significant development. Okay, so we're using the quantization of electromagnetic field. I want to show here that the importance of a noise operator. The noise operator. Okay, if we refer to Scalia-Zubairi's quantum optics, you'll find that for the single mode coupled to reservoir, you'll find that the commutation relation is violated unless you include the noise operator. Without the noise operator, it's violated. Okay, so it's important for the operator to satisfy commutation relation at all times. Okay, for the theory to be correct. Okay? And following that, in our work, we calculated for this two-level system interacting with vacuum radiation, just two-level and vacuum radiation, and no laser. Okay? And we show that this operator A and AK we show that it will be able to satisfy the commutation relation if we calculate all the terms correctly. Okay? Take note, this we know how to calculate the noise operator correlation using the Einstein's fluctuation dissipation and this diffusion coefficient theorem. But this term is a bit tricky. So we find that this commutator, they are not zero. These two commutators, they are not zero. And the fact that they are not zero is important to satisfy the commutation relation at all times. Okay? Even though they are not zero, however, if you take the expectation value, they are zero for the case of the vacuum thermal radiation, because of the expectation of the F equals to zero. So from there, we carry on to, we know how to calculate the quantum Langevin with the noise operator correctly. We extend the single particle double Raman system to the case of from CW to pulse, to all the pulse driven by pulses. So now the pump and the control lasers are just not CW. It can be any pulse, any temporal pulse with a chirp or any shape. Okay? So we have in this work we have got the exact result. Okay? Okay? Using this double Raman scheme, using the same control, and then we compute we find the solution. For the K is the photon operator for the Stokes. Q we don't write it here, is in the same way. Q is for the anti-Stokes, and it has a sum over all these coefficient 1 to 16 that numerically can be solved. Okay? This K coefficient can be solved numerically, and these operators we have to take care, calculate term by term. Okay? So we compute the Cauchy-Schwarz inequality. We want to show that it's less. If it is much more than 1, then there is non-classical. And here is the result. We have the G2, and these dotted lines are the overlapping pulses of the lasers control and the pump pulses. The top one, they are counterintuitive, means the control laser comes before the pump laser, and we compute the G2. And this part, the difference are all different chirping effect. Also want to see how is the effect of chirp. So we find that the G2 is large when the pump is chirp, only the pump is chirp. Okay. At the bottom panel, we compute the intuitive pulse. For the intuitive pulse, the correlation, the violation is less. So the counterintuitive sequence of the pulse gives rise to greater violation of the Cauchy-Schwarz inequality. Here it shows if the control is chirp instead of the pump, then you have a larger violation, okay, of the larger non-classicality. Right? So these are the interesting result of the effect of the pulse laser instead of using CW to enhance the non-classicality of photon. Okay. From there, we can extend to one-dimensional propagation case. Means we have propagation in one dimension, z along z direction. First, we consider the two-level system. This is a two-level system. Okay, you can do this, but I will just mention that this we have done, but this is not the most important result, so I will skip it. Yeah, I will skip it. You can refer to the paper. We just need to note that we can have a very larger G2. We have plotted the G2 for different propagation length. For larger propagation length, the G2 coherent time will be larger when the inversion is positive. W is the inversion. When the inversion is negative, then it's the other way around. If we increase the length, then the G2 coherent time will become shorter. Okay. We also done for the cascade scheme. Yes, cascade scheme because we want to compare with parametric down conversion. We want to use a quantum formalism, quantum Langevin formalism to compare with the parametric down conversion that generate entangled photon pairs. Okay. So this is the usual scheme. So we have used the quantum Langevin and we find that the G2 is also exponentially down. There is no anti-bunching. Okay, there's no anti-bunching. Basically, all these terms are B are actually with the boundary operators and without the noise operator. Okay? And this is the case of a large detuning, large negative detuning. But if we have a resonant, when we have a resonant case, then we'll find that anti-bunching will come when the pump is strong enough. Okay, when the pump is increase, then you have anti-bunching. Okay. In the case of cascade, this is for the small optical density, and this is for the large optical density. Qualitatively, there is no significant difference. Okay. So almost at the same time of the work on experimental work of Lukin's group with the double Raman system, Steve Harris from Stanford came up with another experiment for this double Raman scheme, which generate the curve of a G2 coincident rate. In their experiment, they find anti-bunching and also oscillation, and they have done some theory to explain their result, but that was not published. So we try to reproduce their result. We try to reproduce their experimental result by doing a full quantum Langevin theory with propagation included. So in their case, they have a backward geometry. We have generalized extend to both forward and backward geometry. Take note that when we have propagation, we not only have spontaneous Raman, but we also have stimulated Raman. Okay, and we also have this resonant Raman. Okay, resonant Raman and also resonant force. All these effects, they are included. And the slow line also, everything is included. Right? And we can also include the phase matching condition also. So this is their experimental result, and this is our theoretical result. So we try to fit as close as possible, and there is no fitting parameter. We don't use any fitting parameter, but we get quite close. Okay, quite good agreement. And here is the theory. We use the Hamiltonian four-level system with the atomic level, radiation, and the interaction. So this is the interaction with vacuum that will give rise to spontaneous emission. This is the pump laser, control laser, and this is the quantum macroscopic field of the Stokes and anti-Stokes. So this, we take care of this as an operator. We want to solve for this Stokes and anti-Stokes field. So we are using Heisenberg-Langevin equation coupled to Maxwell equation, and then we derive the linear couple equation in space and time, then solve for the quantum field in terms of the noise operator and the boundary operator. Okay? So the solution is essentially exact within this approximation. From there, we compute the two photon correlation and study the non-classicality like G2. We neglect the center of mass motion. We neglect collision, transient pulse, and also the multiplicative points. So basically, it looks like this for the atomic equation, and then the noise operators. The full expression can be derived. Then we couple to the slowly varying envelope approximation Maxwell equation. We put in the polarization, the atomic part, with the sum over all particles. And then we convert the many particle equation to the continuous wave by using this delta function that we sum over. Right? So we have a new atomic operator and the noise operator that depend on space, Z, and time. So we have four equations of the fields, quantum field, microscopic field, two Stokes and two anti-Stokes, including the conjugate, coupled to the 16 atomic equation. So we have 20 couple equation. But we cannot solve all the 20 equation. We have to make some approximation. The population we consider as a steady state. Okay. And then here we neglect the multiplicative noise. Whenever we see the product like this, we will decouple we take the expectation value of the atomic operator. We keep the quantum field as it is, and this we put in the steady state solution. So from there, our 20 equation reduced to essentially this 6 equation that can be solved exactly. So we solve using Laplace Fourier transform, then we get this couple parametric equation for the Stokes and the Stokes S and the anti-Stokes. And they are connected to the field by this, and this F are the noise operators. Okay, so now this couple equation can be solved exactly. The microscopic expression for the G, S, G, A, K, S, K, A, I not shown here. They can be obtained. Full expression can be obtained on the microscopic parameters that depend on the Heisenberg and Langevin equation. So here, the noise, we have the noise part and the boundary part. The boundary due to the dependence on the boundary condition of the extended median. Okay. Here, just to note that the boundary part is important. It describes the first layer atom, the first layer at the Z naught. If let's say the boundary is at Z equals to 0, at the first layer atom 0 plus, that's where this boundary term will be important, because it gives rise to the stimulate the subsequent atom to initiate the superfluorescence and stimulated emission. So here the boundary part for the Stokes has two components. It depends on the boundary of the anti-Stokes as well, and also, of course, the boundary of the Stokes, because these are the parametric system. Okay. So this is a boundary term, and the coefficient size, all these are given in term of, it can be written in terms of the hyperbolic cos and sine. The theta are actually dependent on the atomic parameters, the alpha also. The noise part is also an operator. It is quite symmetric, depend on the psi. Okay. And here the F is the noise operators. Okay. Or the noise operator. So from this solution, we can compute the G2 by using the commutation relation for the noise operator, okay, and also for the macroscopic field. So we can compute the G2. It can be composed of the boundary part, the noise part, and the mixture. So the full expression is the sum of these three. But we have calculated all the terms exactly. Okay. So now we also can calculate the Cauchy-Schwarz inequality, the normalized term. So the violation will mean this quantity is greater than 1, but it's not necessary entangle is not a different definition. We can also compute the self-correlation between the Stokes, self-correlation between the anti-Stokes. So everything was computed. And then here's the result. The G2, we compute, we compare the result for single atom and then the case for amplifier with propagation extended medium, without noise operator here, and then with noise operator. So it seems that all the results agree qualitatively. It shows that there is no. It shows that there is no need for noise operator, right? For this kind of parameters. Okay? No decoherence, means the decoherence of the ground of the between level B and level C. Okay? However, when we have decoherence, okay, when we have decoherence, gamma BC is not zero, then we will see that the result without noise operator is very different in the case of weak field. Okay, in the weak field is different. So obviously the result with noise operator is correct. Okay, because it agrees with the single atom case. Therefore, it shows that the result with that it shows that noise operator is necessary, is important, especially for the case of the presence of decoherence. When we increase the field, the control field, then all the results agree. That shows that noise is not needed. Okay, so that means when we get result that agree with experiment, doesn't mean that our theory is correct. Okay, it just seems that we are lucky. We are lucky to show that in that certain parameter regime, we get the result that agrees. Okay, like in this case, but the theory is not correct if we don't have the noise operator. All right. So to summarize here is just a picture to summarize the importance of boundary operator and the noise operator. Okay. So here is how it shows. First layer atom, we have spontaneous emission, stimulated emission subsequently. The term with the superscript N means we neglect the noise operator. The term with the superscript B means we neglect the noise operator here. Okay. So the full theory means we have to include the quantum electrodynamics, means we have to quantize the field as well as including the noise operator. So the noise operator is compatible with the fluctuation dissipation theorem and due to the quantum electrodynamics. And the commutation relation is just quantum mechanics. So quantum mechanics alone is not enough. We need to have quantum electrodynamics of the vacuum. So this is a summary of the result. That the quantum theory without noise operator has been widely used in many studies, but actually they are not correct. Okay. So the correct description is we need to make sure the result is can depict in the case of strong field, weak field, with and also with decoherence and finite sample. So if this region, three cases can be met, then we can be correctly described. We need to have a noise operator. Okay. This is to show the ratio of the noise part divided by the ratio of the boundary part. It goes with the number density. When the number density increases, the contribution of the noise grows. That means the effect of the boundary become less and less important. Okay. All right. So this is the summary. The full calculation of the photon correlation using Heisenberg Langevin with propagation effect, proper noise, quantum noise included, include dissipation, dephasing, inhomogeneous broadening, density effect, and spatial propagation, but only in one dimension. Raman photon pair shows non-classicality even though in external medium, but it has to go down. It's not very intense for large distance. Correlation can be controlled by laser field, and anti-bunching depend on the sample length and also the pump field. So these are potential applications. Now we extend to microparticle Raman and also compute the spectra and also the G2. So we consider very simple geometry, which is spherical and still double Raman. Okay, so how are we going to solve this? Basically, we start with this Maxwell, homogeneous Maxwell wave equation. Polarization, we have to integrate, we have to solve for E. So the solution is the operator, we put polarization operator, E operator. And then here is the formal solution for the spherical, which includes the polarization here. Okay, this is kind of well-known solution. It means we can find the electric field emitted by the spherical particle, put in the polarization operator, everything. But now the electric field will depend on the position of the detector. Okay? Can depend in all angles, theta, phi, as well as r. Okay. This actually the detector, the big R, the small r correspond to the coordinate inside the particle, microparticle. Okay. So we can get a solution by Fourier transform in frequency domain. We put in the solution from the 16th equation, Heisenberg-Langevin. We plug in here. Then we can compute the spectrum. The spectrum is just a simple correlation function between the field. Okay. We can compute the spectrum of the anti-Stokes, and then and also for the Stokes. The N is the normal order, the anti-normal order is this. So both are actually not very much different. Okay. And the nice thing about the microparticle is that the laser field inside the microparticle is not homogeneous, and this can be included. Why is not homogeneous? Because as the laser goes into the particle, there is self-focusing diffraction effect, and this can be taken into account by the Mie theory. Okay. So this is an example of the plot of the field distribution. Okay, now this spectrum of the for several cases. Raman EIT is the one with I showed just now the scheme, spontaneous Raman followed by resonant Raman. Asymmetric resonant means the two driving fields are different. The two driving fields are different, and two driving Rabi frequency are different. Symmetric resonant means the two Rabi frequencies are the same. So we have two different Rabi frequency. You can have an additional peak, and in this case, it's just the mono triplet here. In the case of Raman EIT, it seems that the spectra is not very impressive. Just to have a double peak due to the EIT. Here, what we need to notice is as the size of the particle increases, the peaks are shifted a bit, become wider. This is due to the coherent effect by the outer town splitting, and also broadening. The peaks become broadened. Okay. Now we can see further effects of the particle as we increase the size. In the case of they become anti-symmetric. There are very strong narrow peaks coming up at some radius, some certain as the size increases. So this is a microscopic effect. So similar feature. So there are all the fine structures that increase due to the size of the particle. They are actually due to the power broadening and also whispering gallery effect. Okay. The scheme for the resonant and the non-resonant, I can't really see the top. Okay, this is a weak resonant. Yeah, when we have a strong resonant, then we have the peaks are big. There are mono triplet peaks here. But okay, here is the angular dependence. So depending on the detection angle, okay, when the angle is 0 or 180 degrees, there is essentially no signal. So near, but it's not maximum also at 90 degrees. Okay. Now, we can skip all the spectra and now go to the G2. The same scheme, now we compute the G2. The G2 for the, see how the G2 varies with the interparticle size. So the G2, it seems that is vanishing. This is the correlation between Stokes and anti-Stokes. This is the correlation between the Stokes and anti-Stokes. Okay. So that means the macroscopic effect has caused the quantum correlation to vanish. Okay. At high density is even faster. The self-correlation, it seems that the correlation time has been reduced as the particle size increases. And this is, I can't see the top. Okay, this is symmetric resonance. Yeah, the result is also not impressive for the resonant case. Okay, because the G2 is very small. It's almost close to 1. No, so and it is going down, and for the last particle goes to 0. Okay. However, if you are interested in the self-correlation, for the self-correlation, we find very interesting. The correlation time is increasing as a particle size increases. Okay. And this is the case of symmetric resonance. Just now was also the same, but this is a weak field. This is a strong field. Okay, when you increase the Rabi frequency, similar feature as a weak field, no correlation for large particle, but the self-correlation, we have a very at some size, certain size parameter, the correlation of the Stokes and anti-Stokes, the correlation time becomes very large, super long, okay? Especially at high density. Okay? So this may be interesting if can be demonstrated experimentally. The same qualitatively the same for the for the asymmetric feature. This is the reverse. So to be complete, we just put here is a 373, here is 37. Okay. No qualitatively, no different. Then we also plot the angular dependence. The angular dependence of the correlation means depending on the detector or angle. In the forward, mainly the signal is strong, but the backward for the high density, it seems that the correlation time is going down. Okay, but mainly somewhere in the middle, there is no much effect, not much different. Okay. So this is basically how the Raman EIT is affected by the size of the particle and also the angle of the detection relative to the pump and the control field. Right. Okay. So finally, this angular dependent is for the symmetric resonance is strong only at a 90 degrees angle of detection. For other angle, detection is weaker, okay? Especially for high density. So there is just not a simple way to tell about this angular dependent and the role and the string size dependent. All the pictures show everything. The pictures was 1,000 words. Okay, so to summarize, double Raman scheme is useful for generation of non-classical light and with coherently controlled photon correlation. We have done rigorous theory of Heisenberg-Langevin with noise operator. We show that proper noise operator is necessary to correctly study quantum correlation. Finite transient pulse is interesting as it can enhance the quantum correlation. And this is also relevant in the case of storage and retrieval in the case of quantum memory. We need to use pulse, not CW laser. Okay. So then the dipole-dipole interaction has a significant effect on the quantum correlation. And then the large propagation length and finite microparticle will reduce the cross correlation between Stokes and anti-Stokes. However, it will extend the correlation time of the self-correlation, the Stokes self-correlation and the anti-Stokes self-correlation. And this theory could be applicable for various schemes and studies in quantum information technology. We have used also the theory in the quantum plasmonic. The whole thing we extend to include the matter particle, but there's no time to present it here. Maybe sometime in the future. So thank you very much for your attention, and thank you the organizer and Professor Pasanta for organizing this. Thank you all.
Thank you. Very, very nice talk. Thoroughly enjoyed it. And open for questions if there are some questions from the chat box.
Yeah, there is one question in the chat box.
Please read it out.
Okay.
So, when the externally injected fields are non-zero, and how do we calculate the boundaries of quantum fields?
When the external is, I missed the first part. Professor, can you please repeat? Okay.
Sure. So the question is, when the externally injected fields are non-zero, and how do we calculate the boundaries of quantum fields?
Oh, okay. Thank you. Yes, in our case, we neglect any injected Stokes and anti-Stokes external field. Yes, it would be good if we can include that. Yeah. If you include the externally injected Stokes and anti-Stokes field, then the E operator, E naught, ES naught, and EA naught will be a classical injected field. Is no longer the quantum field. It's like a laser or something like this. Yeah. We have not done that. Yeah. Thank you.
I have a question, Professor Wade.
Yeah.
Your the equations in the semi-classical limit, some of these multi-level systems satisfy soliton equations. There are soliton solutions for electromagnetic field and also the electron creation or annihilation operators in the semi-classical limit. I see in your field configuration, some of them do look like solitons.
Which one? Huh?
Yeah, some of these field configurations look like, periodic soliton solutions one finds in not at the quantum level, but at the semi-classical level. Second part, you showed some of the intensity plots towards the end. Yeah, these equations are quantum equations. They are, the fields which you get, some of them look like solitons. Yeah. Yeah, these coupled equations. Yeah, these kind of things. Will there be solutions which look like solitons or no?
I have not looked into the soliton, but I think this is we neglected the transverse propagation effect. In the propagation equation, we have the transverse part, which is the x and y. We are not included. Maybe if we include that, we may have the maybe self-focusing or Kerr effect.
Okay. Yeah.
This is only along z direction.
Right. Yeah. Thank you. Thank you very much.
Thank you. Yes. Maybe we can look into this. Yes. Thank you.
Yeah. Is there if there are no other questions, let's thank Professor Wee for a truly wonderful talk. Very nice talk.
Sir, you can stop sharing the screen.
Oh. Okay.
Yeah.